my intention is for it to be relatively informal, along and have a chat. My intention is for it to be relatively informal. As Ian said, when he asked me to do this, I said that it's not a problem, because literally, I would say less than a month ago, some of our executive directors were looking for an idiot's guide to developing an offshore wind farm, and I don't know why they asked me, but there you go. Anyway, the presentation, I suppose, is that it's actually, it was written and designed to be read rather than presented, but it still provides a useful context in terms of just running through the stages and so on. So just get my mouse in the right place. Hopefully this. So that's the first problem. That's better. Okay, so I suppose the first thing to say is that this process of developing an offshore wind farm is not a fast process, and you can see there just in terms of the milestones. I'm just going to drag my my screen out of the way a wee bit. So ultimately, you can see that we're probably looking at best a nine-year development cycle. So from the day and hour that we start the notion of trying to find the site until the point that we get it built and connected, you're probably looking at 9 years, and that could be optimistic. So certainly we're working on a project off the east coast of Ireland at the minute that started off. There's no sign of it. It's likely to be operational by 2025, and that project started in 1999. So that can give you an idea of some of the headaches. To be fair, that's unusual, but I'd say 10 years is not unusual. So just to run through that briefly, the first year is mainly around actually trying to find the right site. And you might look out to sea and say, well, look, sure, it all looks the same as far as I'm concerned. But there are quite a few differences that are important that we need to figure out. Second couple of years then are around the environmental surveys, and that's no different to doing any work onshore, or in fact any significant infrastructure work. So if you're building a new road, you would probably have to do a minimum of 2 years data gathering and environmental surveying. Once you get to that point, so you have hopefully gathered up the information that you need, the next stage is to produce an environmental impact assessment report, and that's effectively gathering up all of that information you've gathered up over the previous 2 or 3 years and presenting it in a way that can be assessed by the relevant authorities. Assuming you get a consent, then the next 2 years-ish are around really the heavy engineering, if you want to call it that. So it's actually about making sure that the project that you have got a consent for can actually be built. And look, that, you don't need me to tell you that once you operate in the sea, it's a lot more complicated than it might be onshore. And then typically, at best, you'll build out the project in 2 years, and it might take 3 years, and then you get to commercial operation. So as I say, to recap, you're probably looking at a 10-year development cycle in terms of getting from start to operation. So look, I just intend to run through that process and give you a sense of where that's at. And so the first stage is actually trying to find a site, and most of that site screening, as we would refer to, is in the context of constraints analysis. Okay, and some of those constraints are technical, so that some of you'll recognize that area of water, and that's just one that I plucked out because we had access to it from a piece of work we're doing recently. And you can see there, obviously that's a standard maritime chart. It gives things like depths and navigational features and so on. And there are certain things that can't be used as a site. So the two significant black lines running through the middle of the slide, those are effectively marine separation zones that are effectively the equivalent of a motorway for marine traffic. Okay, and you can't really do anything that interferes with them at all, because they're protected actually by international treaties, so they're not even a UK issue. That's in the context of that piece of seaway, that's probably the busiest piece of seaway in the world, and so you cannot interfere with the shipping as it's going through there in terms of those two lanes. The sort of the ship shape to the left of those lanes is actually a current operational wind farm, so obviously it's out of action as well. And then there are other things that are important. So one of the things that's really important is what's called the significant wave height, which is, if you like, how what's the highest average wave that you're likely to encounter at that point. And it's not that you can't install the turbines and operate them in significant waves. It's that the turbines need to be accessible from the point of view of maintenance and operation. And so if the wave height is too significant, it can't be, the turbines themselves can't be accessed. Actually, so what's below the sea level is also really important in terms of the seabed itself, because it's like any other foundation onshore. You need to have the right soil conditions to actually try and create the suitable foundation. And then separate to the technical stuff, you have all the planning assessments. So you're trying to figure out, so will this thing be acceptable from a visual point of view? Will it be acceptable, as I mentioned, from the shipping point of view? There are, in the same way onshore, there are protected areas offshore. So the special protection areas, for example, European designation usually for birds, not always, but usually. And then other policy. So for example, in the UK at the moment, one of the biggest challenges is making sure that the project doesn't have an unacceptable impact in relation to radar. And that's from a civilian point of view, but also from a military point of view as well. And the other thing, of course, is that you're trying to figure out where you're going to connect one of these projects. And suffice to say, at this stage, we would be considering a project perhaps up to 1,500 megawatts. And so that's a very significant grid connection that's required. So that's about the same scale as any modern gas-fired or nuclear power station. So you need, it's not something you're going to connect onto your local 33 kV network or your 110 kV network. Mouse keeps leaving me, apologies. So moving on then, so once you have a reasonable idea of a site and where you would like to go, then the next thing to do is to carry out this environmental survey work. And this is a long-term commitment. Some of it can be done from the sea, some of it can be done from the air. And it's, from the point of view of anybody in the locality, they won't notice much going on for 2 years because, there might be a ship in the area similar to the one on the screen there. Or there might be an airplane traversing the site on a monthly basis, but in the context of what's happening on a day-to-day basis, people won't notice much difference. So there won't be much to see. What are they trying to figure out? They're trying to figure out where or what's happening in relation to marine mammals. They're trying to figure out what the potential impact might be in relation to fish and shellfish. And the big one, and the one that's having a significant impact from a UK point of view in terms of offshore wind, is the impact on the bird population, or potential impact on the bird population. The other areas then that tend to be significant are where the sea meets the land, because you obviously need to land a cable on shore, and that cable typically will come across or come ashore at ideally at a sandy beach. And you can imagine from an environmental point of view and also from a social point of view, that may not be the ideal thing. You can imagine if somebody rocked up with a lot of heavy equipment on the East Strand at Port Stewart or Port Rush and decided that they wanted to pull cables and diggers and all that sort of stuff. So you can imagine the impact that can have on the local community. So quite often the onshore connection will be at least as significant as any other infrastructure assessment. So, it wouldn't be uncommon to have maybe a 30 to 60 kilometer connection from the shoreline to the main grid connection point, so the main infrastructure. And so when you're doing that, that's a significant assessment as well. Anyone that has any familiarity with the north-south interconnector in terms of the work that has had to be done in relation to that and evaluate the impact on humans and on the environment will know that that piece of work should not be underestimated at all. It kind of goes without saying that there's no point in building an offshore wind farm if you're not going to have the wind to actually make it worthwhile. And so you need to get a handle on what type of resource is there. In the past, what would have happened would have been there would have been an offshore platform installed, and there would have been a fixed met mast put on top of that. You can imagine that in itself is a very expensive activity. So if you want to build an offshore platform and build a mast on it, even though the mast in itself mightn't be that expensive, the platform that it sits on will be extremely expensive. So this is a relatively recent innovation, this notion of LiDAR, which is used to measure the wind. It's more straightforward. It's less expensive. You can see there it's a relatively small device that sits on the shore, or sorry, sits at sea, anchored to the seabed. It is something, as you can imagine, it's something that you just can't plant out in the middle of the ocean. It has to be properly consented, and that obviously because it's effectively a hazard to shipping, and so it needs to be properly notified and so on. The other thing that's important is that it needs a correlation. So the met mast itself ideally will have another met mast as close as possible at an onshore location, so that you can get a good correlation. And quite often what will happen is that onshore mast then will be collated to somewhere that has a long-term weather assessment. So, you know, one of the most popular ones are the airports, where you have a long-time assessment of wind speed over quite often decades, and that means that you can make a good attempt at a resource assessment in the context of trying to figure out how much wind you're going to get offshore compared to the requirement that you'll need to make the project profitable or not, as the case may be. I think that this is one of the things that everybody involved in wind energy production, onshore or offshore, has learned to their cost. It's something that's not done well as a rule. I think the industry is getting better at it, but it's something that we all need to be much better at. I'm not sure if any of you have been keeping an eye on RTE television. There's been a program on the last 6 weeks on a Sunday night called the Southwesterlies, which was about a Norwegian company planning to develop. It was a drama series. A Norwegian company planning to develop a project off the southwest coast of Ireland, and just about it was kind of highlighting the things that can go wrong if the community engagement isn't done properly. Like for us, probably the key stakeholder, the most important stakeholder of all, are the fishing community. And look, understandably, fishermen will be nervous about anything that we propose to do offshore, because depending on the type of fishing that's carried out, it might restrict them from what they typically do. It doesn't tend to be a major problem if it's shellfish or if it's pots. But once it involves any degree of trawling, it can cause a problem because of the cables that are on the seabed floor. So that's a potential concern for them, because they can potentially lose their habitat or their working area. I suppose the upside of that, and again, you might be familiar that David Attenborough has a documentary on Netflix at the minute, and one of the interesting findings is that where they have done analysis on offshore wind farms, they've discovered that in many cases they become a haven for wildlife, including fish. So what, you know, and this, you know, the fishermen will say, well, you would say that, wouldn't you? But ultimately, what they found in the longer term is that actually the wind farm, because it's a haven, actually helps increase the fish stocks that are in the locality. So there is a definite impact in terms of where the fishermen can go, but they're in the medium to longer term, there's a potential benefit as well. I mentioned earlier on just about the impact. As I say, that beach on the top right-hand corner of the screen there is an ideal, from our point of view, is an ideal location to land the cable and bring it ashore. But the people that are walking up and down the beach, and those that are doing their daily swim, and you know, the dog walkers and the people training race horses or whatever, none of those might agree with me that that's a really good place to land the cable. So it's important that they understand what we're proposing to do and why it's important. As I mentioned earlier on, that, you know, you might consider an installation that could be 60 kilometers long in terms of a cable, And typically now those cables, because of all the problems exist with overhead lines, typically those cables are buried, and they're usually buried in the road. So that again, that can cause kind of knock-on impacts on the local community, and so they need to be aware of that. And it's up to us as developers to manage that process to make sure that people are not significantly disadvantaged by the work that's being proposed. And look, you know, that bottom right hand of the screen there is an onshore substation. And look, I've been involved in wind production now for wind energy production for a long time, and there are ongoing debates as to whether people like or dislike wind turbines. I don't think I've ever heard anybody saying that they really like the look of an onshore substation. So, you know, they're always viewed as a negative. They're a necessity, but they're always viewed as a negative by local communities, and again need to be sensitively handled. So that's a big deal, and look, that needs to be done early in the process, because you just stack up problems down the line if you don't deal with it. So the environmental impact assessment report. Anyone that's had any experience of working on environmental impact assessments will know that that's a reasonably standard document, and you just have to go through the grind of producing it and making sure that you carry out the necessary studies and work through the potential impacts from an environmental point of view. So, you know, that those headings are reasonably standard. So some of the stuff would be applicable if it was an onshore. You know, an onshore development. Some of it would be applicable, for example, if it was a new road development. Obviously, other things are not, in terms of you know, you don't need to do too much intertidal assessment when you're building a new road, for example. So I mentioned earlier on about all the survey work. So we talked about fish, we talked about mammals, we talked about birds, we talked about shipping navigation. So basically, what we're trying to do here is demonstrate that the environmental impact of the new project will not be something that is unacceptable. Like no one, myself included, will ever say that building a project of this scale will not have an environmental impact. Of course it will. So the question is the impact acceptable? And quite often it comes down to the impact on, you know, it can be down to the impact on particular ecology or birds or whatever, and whether or not you can balance the impact on one versus the benefits of the other. So I think at this stage you're starting to get into what you might call the really expensive stage. So it wouldn't be typical to do this until you had a consent for the project. And so remember, you know, if you remember back to what I was saying at the start, you're probably looking at you're 4 or 5 years into a project at this stage, and you hopefully are going to get a consent from whoever the relevant authority would be. So quite often, because of the scale of the projects, they're often, you know, they're nationally significant infrastructure, if you want to use that term, and so typically they're dealt with directly by the government. So either the UK government or the Scottish government, or again, some of the projects I'm working on, the Irish government directly. So the application is made directly to them, and they will make a consent or not. And assuming you have a consent, then you really are getting into the point of trying to figure out, well, can we actually build this thing? And bear in mind now that, you know, for a project of a reasonable scale, so let's say for a project of around 1,000 megawatts, up to the point of getting planning, you could have spent in the region of 40 to 50 million just actually getting a decision on where that project is. It good to go or is it not? Okay, but then you're into, you know, really expensive individual activities, and the first one of those is effectively the geosurveying. And there's two types of geosurveying. There's a geophysical and there's a geotechnical. And in simple terms, the geophysical is the stuff that you can do that's non-intrusive, whereas the geotechnical tends to involve some kind of digging or drilling. Geophysical is relatively inexpensive. Okay, now you're still talking about renting vessels and all that stuff, and that's not cheap, but compared to the geotechnical stuff, it is certainly less expensive. what you're trying to do is find out as much as you can without actually doing anything that's too intrusive or too expensive. So that's accurately determining the depth of the water. It's also trying to get a sense of what's below the ground. And I remember back in the day when I was in Greenmount 15 years or more ago, whenever there was work being done at that stage in relation to precision agriculture, and effectively, they were dragging similar devices across the field to try and get a sense of the degree of compaction and the nature of the soils from the surface, and that was done, through echo sounding or other types of electronic measurements to just get a sense of what's going on below the surface. And this is no different. Okay, so you're effectively towing a range of devices either on the surface or just below the surface to try and get a sense of what's going on at the bottom, at the seabed, and then below the seabed. But truthfully, it'll only ever give you an indication. And so you're then into the stage of a full geotechnical campaign. And so you're into specialist contractors with specialist vessels. And those vessels will be doing taking samples or doing things like cone penetrometer testing, which you might be familiar with from an agriculture point of view, or the most expensive one is which is the drill itself. So typically on an offshore project, at the very least, you would want to drill one borehole at each turbine location. You'd want to drill boreholes at the substation location, and then you would want to be drilling boreholes along the export cable route. So again, you don't belong in that geotechnical work. We're racking up a bill of a few million, 3, 4, 5+ million is not uncommon in terms of the work, or sorry, the cost of doing that survey work because of the vessels and so on. And look, that's very dependent on weather. You need the right conditions and so on. So again, that's one of the things that can slow down the process. So then we get into this, and I'd never come across this term until I got involved in offshore wind and this notion of front-end engineering design. And look, this is kind of high-level decisions and some of the early stage engineering that needs to be done at a relatively early stage to try and figure out how much the project is going to cost. So I suppose just to put that in context, so we're currently working on a project at the minute in Scotland. That's give or take 500 megawatts, and in terms of the cost of developing, give or take, is 1.5 billion. Now, so that's a very significant investment in terms of the amount of money that's going to be spent, and you can imagine that there aren't too many companies that can finance that type of project direct from their own internal resources. So most of these projects are financed, and that means that they have to get to a process called financial close, final investment, and that process is around trying to figure out, so how much is it actually going to cost us to build this thing, and then how long will it take us to get the money back. And the way that offshore wind farms are funded currently is they're funded under something called a CFD scheme in the UK, and that CFD scheme is contract for difference, and it's about effectively guaranteeing a price, if you like, for the offshore project. It's typically that price is guaranteed for 15 years, and the interesting thing is that price today is very close or below the actual market price for electricity. So in other words, the real subsidy, if you like, for offshore wind farms in the current market is actually very low. If in some cases actually no subsidy being paid now at all. But the thing about that contract for difference, and the reason that it's important, is that it provides certainty for the first 15 years in terms of the energy price. So you take out one of the big variables that can happen in terms of the fluctuation in the electricity price. So this front-end engineering design is all about trying to figure out what price does the project need to get to make sure that it's successful, because it's typically on a competitive auction basis. So the projects that are competing to get that support, not all of them will be successful, and so it's the people that bid the keenest price will be successful. So just to talk about some of the big technical decisions. Foundation is a key one, and I'll talk about that more in a minute. Foundation is the one that gives us, and most of the time gives us most of the headaches, because it's stuff that's under the water. You're trying to figure out what the seabed conditions are like at the bottom of the sea, and so there's all sorts of headaches associated with that. Turbine choice is not too bad. The good thing about turbines is that offshore turbines now are significantly bigger than what's available onshore. So as things are working today, we're working on the assumption of installing 12 or 14 megawatt turbines, over 220 meter rotors, so 110 meter blades at least. And into the future, we're probably looking at something like 17 and maybe pushing it as far as 20 megawatt turbines. Now, the typical onshore turbine that you'll see installed locally in Northern Ireland, in terms of on a wind farm, now not one of the on-farm turbines. The typical turbine you'll see on a wind farm in Northern Ireland is 3 megawatts. So it's a significant increase in scale when you go offshore. But ultimately, the turbine, the fundamental technology behind the turbine, is similar to that's used onshore. It's just the turbines are marinized to stand the very difficult conditions. High voltage substations, nothing. The issue is primarily the fact that you're having to offload such high volumes of electricity. That's the biggest challenge. Then cabling is a big deal, and there's two types of cabling. There's the cabling that runs from the offshore substation onto the beach landing, and then there's what's called the array cables, and that's effectively cables that are laid on the seabed to connect each of the individual turbines back to the substation itself. And then the last thing is around, which is not often considered much in the context of onshore development, which is a big deal offshore, is how you actually go about installing these things. And we'll see a few photographs in a minute that actually describe some of that technology. So just, I suppose, to talk a wee bit about the foundation types themselves. So anyone that has seen an onshore turbine installed will know that it's a concrete foundation with effectively a tube sticking out the top that you bolt the turbine onto. And the simplest type of offshore foundation is a monopile, which is very similar, except that you literally drive a steel column into the seabed. So you're looking at very significant monopiles. You're looking at 7-8 meters wide in terms of the width of the monopile. So it can either be driven in, or sometimes needs to be drilled. But as things stand at the minute, those monopile foundations will probably work in depths of something approaching 40, maybe 50, but 40 meters depth. Okay, if you want to go any deeper than that, then you're into the next type of foundation, which is effectively a jacket foundation. And those of you that have been around Belfast over the last couple of years, you've seen these without probably knowing what they are, because there was a significant number of them sitting at Harland and Wolff for a long period of time that had been brought in from the Middle East and were being prepared and assembled for onward transmission or onward transport rather to a project called Beatrix, which is a project that was it was a project called East Anglia 1, which is off the east coast of England. So those jackets will be successfully installed up to about 60 meters depth. And obviously the deeper it gets, then the stronger the foundation needs to be, and obviously the more difficult the installation becomes. So you can see that the jacket itself is pinned to the seabed, either by individual driven piles or sometimes drilled pin piles. And the jackets themselves, sometimes you'll see them with 4 legs, sometimes you'll see them with 3 legs. So there are all sorts of designs and insulation. Once you get much beyond 60 meters, you're in bother. It's very difficult to install. Like everything in terms of technology, the boundaries are being pushed all the time, and people are looking at fixed bottom foundation installations at towards 70 meters, but certainly much beyond that, it's a problem. So you're then looking at options for floating offshore wind. Okay, and that does what it says on the tin. You basically put a floating structure in the water and you put a turbine on top of it. You can imagine the challenges associated with that, because just the actual physical weights of the turbines is very significant. But of course, a bigger issue then are the lateral forces that exist whenever the wind blows and tries to turn those blades. And it's like, anybody that's interested in boats, it's like a sailboat where you have a very significant force above the water, and that needs to be countered by something else. So sometimes you have the tension leg platform there that's shown is possible, but not very common. And the industry now seems to be stabilizing on either a spar foundation, which is effectively a heavy, long column that is floats beneath the surface, and it's like a keel on the boat. It's long enough to offset the forces that exist on the turbine head. The other option then is to make something really heavy that sits down in the water, semi-submersible foundation. Regardless of the type, you then have to make sure that they're actually secured to the seabed so they don't move off. It's wrong to say that they don't move, because obviously they go up and down with sea level, and they can move back and forward and so on. But they don't disappear from their base location, if you like, because of the moorings that are there in place. So a lot of work at the minute in relation to floating offshore, and all the technology that's associated with that, the foundations themselves, the cables for connecting the turbines, and the marine solutions. That's a big area of work in our industry at the minute. So a lot of very boring information there, but ultimately it was provided for background information for our directors. But ultimately, the standard approach to developing an offshore project is to subcontract the work or break it up into a number of contracts. So typically there'll be a contract for foundations, there'll be a contract for turbines, there'll be a contract for the cabling between the turbines, there'll probably be a separate contract for the export cable, there'll be a contract for the onshore works, there'll be a contract actually for installation. So because the vessels are so expensive, then quite often the turbine suppliers don't want to take the risk associated with the vessels. So it's up to the developer to carry the risk associated with the vessels. And you might say, well, that's not a big deal. As I say, we have a vessel working in a project in Scotland, literally as we speak. And if you went to the market for a spot hire rate, it's 500,000 a day to hire that vessel. Now, obviously, if you're contracting it for a period of time, it's not anywhere close to that, but it just gives you a sense of that vessel has 300 people, or capacity for 300 people to work on it. So look, there's a lot of work at the point between getting consent for a project and the point where you actually are ready to invest, and making sure that those contracts are all fit for purpose. And as I say, because you're dealing with such big numbers, there's a lot of work from a commercial specialist to make sure that we as the developer are not unreasonably exposed if something goes wrong in terms of the contract. And look, there are all sorts of literally just checked an email there before I come on to give the presentation. And that project in Scotland, there's a vessel out lifting boulders off the seabed to make sure that the pathway is clear for cables. I just got an email from the project manager to say that the vessel has come into shore. One of the crew members has got COVID, and so the whole vessel is sitting parked up now until such times as they're clear to go back to work. The whole crew has to be tested and so on. And you can rest assured that whenever the contracts were being put together for the project, people were not thinking about COVID. So that's the type of stuff that we're up against. I mentioned earlier on about the auction, and look, that's a big deal. So ultimately, the commercial director's job is to try and figure out, so what's the levelized cost of energy? How much does it cost us to produce that energy from that wind farm over the probably 30 or sometimes 35-year life? So he's trying to work that out, or she's trying to work that out. You're then trying to figure out what could go wrong, because obviously you can add up the cost of the turbines and the cost of the foundations and all the rest of it, but you then need to figure out what are all the things that go wrong, and they produce something called a quantitative risk assessment. And a quantitative risk assessment uses fairly sophisticated statistical analysis to try and figure out what's the chances of something going wrong, so what's the chance at a very, at a kind of stupid level. So what's the chances of, one of the vessels actually sinking when it's out there, and what cost will be associated with that? That would have a very high financial impact, but a very low chance of happening. Something that's very real. So what happens if the design for the turbine, what happens if the design for the foundations or the installation of the foundations runs over by a period of 3 weeks or 4 weeks? So what the chances of that are probably very high, but the cost won't be as significant, but you have to put a cost against it. So there's a lot of work done on that to try and figure out ultimately how much will the contract cost overall to get that project from a position where it's all onshore, it's all paper contracts, to a project that's actually generating electricity. Okay. So then you have to try and get people to give you money to build the project, and typically, depending on the level of support that you get for the project, and depending on how good the project looks on paper and how straightforward it looks from a seabed condition or whatever, you could get as much as 80% of the project financed from a group of banks, or you might get as little as 50% financed. And generally there's a relationship between the amount of equity required and the level of risk that's associated with the project. The good thing from our perspective is that there's no shortage of money in the international money markets at the minute for financial or for renewable energy projects. They're seen as relatively safe investments. They're seen as ethical investments, and so banks are queued up to put their money into it. Okay, they obviously have to get their return from it, but generally they're all keen to get involved if you can put together a project that has a sufficiently low risk profile. And obviously generates the right numbers in terms of outcomes. So just to talk about grid connection, and this is a big area of debate both in UK and Ireland at the minute in terms of who builds the grid connection and ultimately who owns it. And so you have all sorts of options. Like one option is that effectively the wind farm developer builds the grid connection and gets it as far as the national grid, if you like. In the UK, for example, it's possible for the developer to build the wind farm and build the offshore grid connection, but the developer is not then allowed to own the grid connection, and that's to do with European regulations in terms of competition. So in the main, generators are not supposed to own the grid connections that connect them to the grid in case they give themselves an unfair advantage. So there's a process in the UK at the minute called OFTO, Offshore Transmission Network Owner, that and that ironically, so the OFTO, the company that owns the connection from the wind farm to the national grid, isn't allowed to be owned by the wind farm developer stroke owner, but funnily it's not allowed to be owned by National Grid either. So it quite often there's a separate company established to take on that ownership. There's a big point of debate in the south at the minute in terms of trying to figure out who should build, own, and operate that connection network between the offshore wind farm and the actual grid connection point. As a developer, ultimately, all I want to know is that we can get it built and connected as quickly as we possibly can. We don't lose a lot of sleep over ultimately who owns it at the end of the day, because if we build it, then obviously the company that comes in to take it will buy it. So it's a return. There's return to us from building that and selling it on. But the key bit is that if we have permission to build the project, we don't want to be waiting for the grid connection. We want to get on and get it built. So I suppose there's plenty of work to do onshore, and thankfully, from my point of view, this is not a problem. Because this is our bread and butter work. We're very used to putting cables in the ground. We're very used to building substations, even though it's a larger scale. But the scale of an offshore wind farm isn't anything bigger than the scale of a modern combined cycle gas turbine generation facility. So it's not, that piece is not a problem, and thankfully it's relatively straightforward. Not forgetting the point that I made earlier on in the process around the whole stakeholder engagement piece, because that's really important. So look, that's awkward and expensive, but it's doable, and it doesn't cause any major problems. as a rule. This is a different ball game now. So up in the top left-hand corner, those are some of the jackets that are used to install the foundations, or sorry, are used to install the turbines in the deeper water. And look, it's always difficult, I think, when you're looking at a photograph to get a sense of scale, but you can see, you know, in the context of the buildings and some of the vessels there, just how big those things are. And bear in mind that effectively, you know, typically the dark colored piece of the foundation is about 50 meters from there to the deck, and you probably have another 20 meters then on top of that again, and the turbine will sit on top of that. So look, manufacturing those things and getting them to place is a big deal. The next photograph in the top right is cable lay, and that's obviously again a big piece of the activity, because you have to put those cables on the seabed, and usually, assuming the conditions are good enough, you want to bury those cables on the seabed. So you want to excavate some kind of a trench. You know, it might be through an actual excavation machine on the seabed, or it might be through high pressure water. But ideally, you will want to bury those cables in the seabed. If you can't bury them, then you're going to have to cover them with rock or some other kind of matting. The next photograph on your right hand side there, so that, as I say, that's the equivalent of trying to bring a cable up onto Portrush Beach. Not something that's ideal from a social impact point of view, but also challenging, a very challenging issue in terms of actually getting the vessel, because that, you know, ultimately you have a cable laying vessel. You want to try and get as close to shore as possible, and then you run the cable in the sea, in the beach effectively, and up through the beach onto a point where you have a connection point. The project, or sorry, the picture on the extreme right at the top right is what's called a jack-up barge, and that system works very well where the seabed is relatively shallow. So, you know, if you're operating at anything up to sort of 40, 50 meters, these things can effectively sail out to where the turbine needs to go, and then they literally drop legs into the seabed and jack themselves up in the same way that a crane, you know, that an onshore crane would do. And then that means that you're effectively fixing, you're lifting from a stable platform onto a stable foundation, and it's not straightforward, but it's not beyond the realms of possibility. So that's okay. You can see there, moving to the left of the screen, bottom left, that's one of the jackets being set into the seabed, and you have a vessel that has a crane on it, lifting those things. So again, in terms of scale, those cranes, you know, the individual cranes are probably 5,000 to 7,000 ton capacity. That's the sort of stuff that they're lifting in terms of being able to handle that. The actual jackets themselves won't be as heavy as that, but you know, but they're definitely in the hundreds of tons number. The really heavy stuff is what you see on the next photograph at the bottom, and that's lifting effectively an offshore substation topside onto the foundation. And you are literally in the thousands of tons there, because you'll have one or two transformers built into that platform, and then all the switch gear and everything else that you need to accept the incoming cables from the arrays and send the cable back out again, in terms of the export. And all of that is built into that. So that we have one of those being built in a shipyard the shipyard in Holland at the moment. Two of them actually been built ready for installation at that project in Scotland. And I say you need a fairly significant vessel to be able to lift those off the barge or whatever brings them along and set them up on top of the foundations. And I think that's probably most of it. You can see the bottom right there is the jack-up vessel lifting the tower section, and then the photograph above that is actually lifting the blades onto the hub itself. So one of the challenges actually, as we get into deeper water, and one of the challenges as we look at floating projects, is that your foundation is floating, and because the water is so deep, you don't get a jack-up vessel that can cope either. So you're effectively trying to lift something from a moving structure onto something else that's also moving. So you can imagine the challenges that that's providing at the minute, and that is a major headache in terms of trying to figure out how to install and operate a floating offshore wind farm where nothing is effectively stable, everything is moving. So nearly there. I suppose just to finish off, the last thing that we need to think about is, and I've touched on it there, is just the operation and maintenance. And so the preparation for that starts at the construction phase, whereby you'll need a facility onshore, and quite often that's not the same place as where you might be running your construction from. So construction, you have very large components being lifted on the vessels and taken offshore. That's not that important when it comes to operation and maintenance. When it comes to operation and maintenance, the critical thing is building it as close as possible to your wind farm, because any time that you spend steaming from the facility to the turbines, it's just downtime. So you want to keep that journey as short as possible. And you can see there, I've mentioned, so some of the wind farms are so far out that they actually will do their repairs and maintenance work or operation and maintenance work by helicopter. So they'll install in some cases, they'll install a landing pad on top of the turbine. What's more common is actually just to have a platform on top of the turbine, and they effectively winch the technicians from the helicopter down onto that platform. You can imagine that's an expensive way to look after turbines if you have to fly out and winch somebody down. Never mind the actual spare parts that you need to get onto the turbine itself. What's becoming increasingly common now is to use these things called service operation vessels, so-called walk-to-work vessels. And these are effectively floating hotels. So they'll sit out there the crew will stay out on that for 2 weeks at a time. And quite often the vessel itself will actually not come back to shore at all. It's maybe not that particularly obvious from the photograph there, but you can see like a gantry or a bridge arrangement. And that's a motion compensated gantry that effectively means that obviously the ship is floating, the turbine's not, but it means that it can attach to the platform on the turbine and then compensate itself for the movement of the vessel as the guys are walking across. And that makes life much more efficient when it comes to trying to service the things offshore, but it doesn't come without its cost. But increasingly, as the projects are getting further offshore, that's increasingly the more common way of looking after the operation and maintenance associated with the projects. So, guys, that's pretty much as I was intending to say, and hopefully I haven't talked for too long. But I think now is probably a good time to stop and take a few questions.
Okay, Guy. First of all, that was absolutely excellent. Thank you very much, as I knew it would be. But maybe just before we switch off the recording, you could tell us, as an agricultural engineer, what is your role in all of this?
So that's a really good question. So the interesting thing is that in my team, okay, so in the team of people that I work with and work for me and stuff. So I have got mechanical engineers, I have got planners, I have got quantity surveyors, I've got electrical engineers. So in the context of what we do, now obviously if you're going to design foundations, you need someone that can do the right structural steel calculations and so on. So you need the heavy engineer and you need the detailed engineer to get involved in that. The other stuff is about adaptability. Okay, so my job is essentially a project manager, and in some ways, from my point of view, obviously you need to understand what's going on in terms of the offshore stuff in the context of some of the stuff that I just talked about. But I'm not an expert in any of that stuff. Okay, but my job is to make sure that I marshal everybody and all the internal and external consultants to make sure that all of the things come together in the way that we need it to happen. And I'll never forget going back to my days working in Greenmount. Sorry, it was actually in Enniskillen, and I took a group of students to JCB. So that would have been, somewhere in the late 90s. And we went to the tractor factory, and the guy in the factory said, he says, we take on whatever number of engineers every year. And he says, ideally, we'll take on half of them as agricultural engineers. He says, I don't need agricultural engineers. He says, I need mechanical engineers or hydraulic specialists or whatever. But he says, I like agricultural engineers. And he says, the reason is because they have a can-do attitude and they can get stuff sorted out. But it's because of what they learn, but also typically because of where they've come from. And I think there's many agricultural engineers now working in renewable energy. And it's not because they're agricultural engineers, it's because the mindset that they've had as agricultural engineers, and that they're given problems to fix and they get on with it and get it started. And for me, as an agricultural engineer, that's the thing that sticks to us as we try to make these projects happen. Bear in mind that we're doing stuff here, a lot of time we're doing stuff that's not been done that much before. So it's not that, you know, you're not building widgets. You're effectively trying to make sure that you can apply engineering technologies to new problems and make them work.
Thanks very much for that, Gary. It's on that great promotion for agricultural engineers and their background. I think we'll just again thank you very much for your presentation. It's been absolutely fascinating, and we'll move off recording now and into a general discussion. Thank you.